We're talking about this next section here in chapter 4. We're talking about section 4, and then we'll talk about some questions from the homeworks. Okay? So just to recap what it is that we're supposed to take away from. So in section 4.1, we're discussing the intricacies of building these inverse trig functions. So why do we have to be really careful about this? Well, for example, if we have something like sine, and I want to turn this into an inverse, what's it going to do? It's going to do like this. What's the problem with that? It's not a function. So what we're going to do is we're going to then just do a domain restriction. So you guys remember this from Algebra 3-4 last year? We did this, at least the students in my class, we talked about restricting a domain to find an inverse. Okay. So the goal here, when we do our domain restriction, is we're going to consider only enough of our function so that it passes a horizontal line test. Because I know if my graph is 1-to-1, or my function is 1-to-1, where it passes the horizontal line test, when I find the inverse, that inverse is a function. So when we consider the graph of sine, what we do is we're going to chop off here and then here. So we're only going to consider the part of my sine function in between those two values. Because after that, we'll have something that's a 1-to-1 function, and we can find the inverse of that function and still have it be a function. So what are these specific values that we cut off? Well, I'm cutting at negative pi over 2 and positive pi over 2. So when we consider sine inverse, the domain is all real numbers. I'm sorry, that's a lie. It's not. It's -1 to +1. Because the y coordinates for sine are bounded between -1 and +1. The range is going to be negative pi over 2 to positive pi over 2. So again, what we did here, for sine of x, we restricted the domain to be between these two values, and the range for sine is that. And you'll notice now that we've restricted sine to be a 1-to-1 function, when I compare the domain and range with the inverse's domain and range, you see they're just swapped, right? Which is what we expect if we have a 1-to-1 function, we find the inverse. We do something similar for cosine and tangent. And this is all spelled out in the text there, what the domains and ranges are for those other two inverses. So for cosine inverse, the domain again is -1 to +1, and the range is 0 to pi. For tangent, the domain is all real numbers, and the range is negative pi over 2 to positive pi over 2. This is all in the text. And really not that material to what we're doing, but it's just wanted to describe why we have to be careful about kind of how we're building these inverses. From a notation standpoint, we're going to use these two notations interchangeably. So I can use sine inverse, or I can say arc sine. They mean the same thing. So just as a notation thing, arc sine was much more common, like 30, 40 years ago probably, and probably previous. Not as common of a notation anymore, but it still exists, still used here and there. But we're just going to use those interchangeably in this course. More often than not, I'll say sine inverse, but there may be problems you'll see that involve an arc sine or something. All right, so if we're asked to find something like the sine inverse of negative 1/2 without using a calculator, what I'm going to want to do is one of two things. One way I could do this is I could use my unit circle. So if I call up my unit circle here, so when I look at my unit circle, which coordinate is representing sine, the x or the y? The y. So if I look at where y is negative 1/2, I have one location here and another location here. So I could say that sine inverse of negative 1/2 is 7 pi over 6 or 11 pi over 6. But as I think it was Andrew, were you the one that was mumbling this? Neither one of those are inside of the range for that function. So if I type this into my calculator, neither of these answers are going to come out. So what I can do is I can just find an angle that's coterminal to either of these that does fall inside of that range. And we had done some homework problems, I think, back in chapter 2, where we did something similar to this. So for example, if I subtract 2 pi from either of these, since they're both, if my range of values is from negative pi over 2 to positive pi over 2, both of those answers lie out here, right? So I should be subtracting pi, minusing 2 pi rather than adding 2 pi. If I do that, I get pi over, I get negative 5 pi over 6, right? Yep. And then I get, what? Negative pi over 6. Thank you. The result that does lie inside of my unit circle, or inside of that range, is this one. So this would be the answer the calculator will give you. Are all 4 of these answers that we've supplied actual answers to sine inverse of 1 or negative 1/2? Yeah. These are all legitimate answers. They all are. They're just not the answer the calculator is going to give you, because the calculator is programmed so that it's actually a function. But all of these are angles whose sine is negative 1/2. We'll talk about what we're going to need, but I want to be clear about the difference of what we're doing right now. So the calculator is going to give you negative pi over 6, probably as a decimal. But all of these, if I take the sine of them, are going to give me negative 1/2. Sophie.
Do the fact that the sine is inverse, does that make a difference at all, or you just try to find the sine inverse?
So the sine inverse what it's going to be doing is it's going to give me an angle measure. So each of these are angle measures. What I'm taking the sine inverse of is a ratio of side lengths, right? And as opposed to sine, where you have to put in an angle measure and you get back a ratio of side lengths. So it's going the opposite direction. Yes? So let me be clear about this. There'll be problems where you'll probably want to do either or. So there is another way of approaching this, and depending on context, we may want to use one or the other. So they're both kind of valuable problems valuable to do. All right. So method 2 involves kind of drawing a reference triangle. So for sine, we know that, again, that our values for x, or for sine inverse, our values for x have to lie in between these two values. So we're restricted to the first and fourth quadrants. Okay there? The reason I know we're restricted to the first or fourth quadrants is because negative pi over 2 is this axis, and positive pi over 2 is that axis. So we're just kind of going in between that. And then using all silly turtles crawl, I know sine is going to be negative in the fourth quadrant, but not the first quadrant. And I remember that sine is equal to opposite over hypotenuse. So negative 1/2, well, call that our theta. So opposite hypotenuse. If I use the Pythagorean Theorem, I get that that side is the square root of 3. And then I just need to make sure the signs on all of these are correct. Remember, these aren't actually side lengths, but they're the coordinates of this ordered pair. So the square root of 3 is my x-coordinate, and the 1 is my y-coordinate. Because we're in quadrant 4, that y-quadrant, or y-coordinate, needs to be negative. And at this point, I recognize that this is a triangle I recognize. It's a 30, 60, 90 triangle. So, in this case, my angle that I'm interested in would be negative 30 degrees, which is negative pi over 6. From the ratio of the side lengths, so the fact that it was 1 square root 3 and 2 as the side lengths, I recognize as the side lengths for a 30, 60, 90 triangle. So just looking at the side lengths. What is the ratio of side lengths for the other triangle that I know? 1, 1, root 2 is a 45, 45, 90 triangle. Yep. So if we're asked to be able to do this without a calculator, we know that it's going to be some kind of either quadrantal angle, where it lies on a quadrant, where it's going to be some multiple of 90, or it's going to be one of these 30, 60, 90, 45, 45, 90 triangle situations. You can't do it without your calculator unless you have one of those others. So we could do this and make it slightly more complicated by combining two things together, like cosine inverse of tangent of 45. If I want to do this without using my calculator, I could use my unit circle to simplify the tangent of 45. So the tangent of 45 is sine over cosine. So what's the tangent of 45? 1. And then using method 1, I could go to my unit circle and find all the places where cosine is equal to 1. Well, there's only one location at 0. And I notice that this is a member of the range of cosine inverse. So we're good. We don't have to do any messing around with that. Olivia? Of course. Does that make sense what we did there? Yeah. I think it's the same. Yeah. A topic students tend to have a little bit of problem with is when we start talking about proving trig identities. Mm-hmm. Yeah. They were my favorite also. So. I don't remember when that comes, if that's 5 or 6, but it's coming. Yeah, it's coming.
It's awaiting us.
I believe so, yes. Again, first time teaching this course with this schedule. It should be a first semester topic. We'll see how it ends up falling. All right. Everybody okay with that? Okay. What if we ask to do arctangent of 2 pi over 3? Well, common sense would tell us, well, inverse tangent or arctangent and regular tangent are just going to cancel each other out. And we're going to be left with this. That's a true answer. The problem is that this is not a member of the range for tangent inverse. Arctangent is the same as tangent inverse. They're just a different notation. That's okay. Everybody okay there? Well, it's not inside of that set, right? All of our answers should come inside of that range of values. Well, no, now we have to adjust that answer. Well, let's see what happens if we did subtract. Well, we certainly wouldn't want to add 2 pi. because we're already bigger than the upper bound. If we subtract 2 pi, though, what's going to happen? It's too small. So what should we be doing here? Raul? They do not. Sine and tangent have different, sine inverse and tangent inverse have different ranges. So, what's the period for tangent? Pi. What did we subtract by?
2 pi.
So if we, again, that was tricky, right? Because normally to find something coterminal, we just add 2 pi or subtract 2 pi, which is correct. That is what you'd want to do to find a coterminal angle. The problem is we're not actually going to find a coterminal angle here with tangent. We need to find something inside of this specific range of values, and that angle actually isn't coterminal, but because the period for tangent is only pi, we can just subtract pi instead, and it all kind of works out. Joanna? Of course. Okay. Is this feeling any better here, people? I didn't do any division. I subtracted. I just subtracted by pi. Because 2 pi is too much. It doesn't actually work. It would if it was sine or cosine. That would be fine. Stop talking, please, guys. If this was a sine or cosine problem, adding or subtracting 2 pi would work. The fact that this is a tangent problem is why we use pi instead of 2 pi.
Okay.
And again, like, you might get an answer where adding or subtracting 2 pi works, but if it doesn't, we can use pi.
Okay, so either or.
Yeah, basically. Okay. What if we wanted to do something like this? What if I wanted to do, cosecant inverse of negative, I should do that, positive 2.5 with a calculator? So which other trig function is cosecant related to? Sine. How is it related to sine? When you say inverse, you really mean reciprocal. Yeah, why is there a problem here? Let's look at what we wrote here and figure out why it's a problem.
Okay.
Because this is what I would expect you guys to have written, is to do something like this. And it's obviously not working, right? We're getting an error on our calculator. What kind of error are we getting? Domain error. What's that tell us? Okay. So, what is the domain for sine inverse? That's the range? So that's not it, right? So we got an error here, and we've now established why we're getting an error. So this that we tried to do initially, not quite right. We were close though. Raul? Yeah, so we have to do, we made the wrong reciprocal. We want to do that. And I think if we do that, that should work. Well, I mean, I asked you guys what to do, and this is what you told me to do. So I figured let's just follow along with this and explain why it didn't work, because it felt like a good learning opportunity. Okay. So that's my answer. Should I write that? How should I write that though? Does that get a degree symbol, or is that in radians? How could we know for sure? Click the mode button. See what mode my calculator's in. Mine is in radians. So what is this 0.4? Yeah. So let's say we want to take or find an algebraic expression equivalent to sine of the arc cosine of 2x. Of course. So what I'm going to do is I'm going to think about 2x as a ratio or a fraction. No. No. It's the other lunch. We still have a half an hour. We're doing fine. Thank you. So I know that cosine is adjacent over hypotenuse. So I can build this much of a right triangle. Everybody agree with that? How can I find that third side of the right triangle? Pythagorean Theorem. So I can have 2x squared plus, let's just call this y for the sign being, equals 1 squared. So when I subtract 2 or 4x squared from both sides, I get this. And when I square root both sides, I get 1 minus 4x squared. Is everybody okay there? Sure. So let's remember what it is that we are trying to do here. We are trying to deal with sine of arc cos of 2x. And we started from the inside and we're going to work our way out. So I started by drawing a triangle. What is arc cosine of 2x going to be then in this situation? It's theta. So what does, hold on a second, that's a good question. How do we know this? What does, stop. What does arc cosine do? It's going to take a ratio of side lengths and return to us an angle measure. What angle measure is it going to return to us? The angle theta here, whose adjacent and hypotenuse are the sides of this right triangle. Everybody's okay with that idea? So we found the right triangle that has those two side lengths, and then we named the angle whose cosine would give us that ratio of side lengths. So to take sine of theta, then, we do opposite over hypotenuse. And we're done. I mean, if you want to write, you can write it over 1 if that helps. We did opposite over hypotenuse to do the sine of angle theta. So to find the arc cosine of 2x, we have to be dealing inside of this triangle. Specifically, cosine of this angle, theta, will give us cosine of 2x over 1, right? So theta is the answer to arc cosine of 2x. It's that theta from that triangle. So to take sine of theta, I just do opposite over hypotenuse for that specific triangle. Done. Okay. Those were the examples from the notes. We've walked through, I think, all of them. I might have skipped one that I felt like was redundant. Do we need to talk about anything from the homeworks right now? I asked you guys to do some of them, right? Do you want to hear the evens right quick? 2 is pi over 4. 4 is negative pi over 3. 6 is pi. 8 is negative 0.193. 10 is 1.791. 12 is square root 2 over 2. 14 is 1/2. 16 is 3.87. Where was it? Where did we end at? 18, you said? Is that the last one we do? Okay. 18 is x over square root of 1 minus x squared. 16 is 3.87. Yeah, I did a dumb thing and didn't print the problems, though, so I have to look at them real quick. All right, find the value in the given interval using the graphing feature of your calculator. Round your answer to the nearest hundredth. Okay, that's not bad. Okay, 16. We want to find cosecant inverse of negative 1.5 on the interval from pi over 2 to 3 pi over 2. And it says use the features of your graphing calculator to do this. So there's a couple of ways you could do this. One of them is to do it graphically. Let's start there. What I'm going to do is I'm going to graph cosecant of x. How do I graph cosecant on my calculator, though? 1 over sine of x. And then I'm going to graph negative 1.5. Notice I'm not graphing cosecant inverse. Not interested in that. And now what I'm going to do is I'm going to graph this on my trig interval. So I'll just do zoom trig. So from 0 to 2 pi, I have 4 possibilities. I have 4 intersections. Everybody sees that? The interval that I want is from pi over 2 to 3 pi over 2. So these negative ones are already out. Everybody agree with that? So pi over 2 is here, 1 pi, 3 pi is here, so the one we're looking for is this spot right here. Everybody agree with that? Okay. How do I find an intersection on my calculator? Second, trace, and we'll pick the intersect command. So I'm just going to scroll over until my cursor is on the left side. Oh, first curve. Never mind. That one, that one, that one. 3 enters and it'll go. Oops. I need to put a better guess. First curve, second curve. And my guess needs to be here.
Why did you pick that specific point?
Because if I looked at my window, my scale is going up by pi over 2. 3.14 divided by 2 is 1.57 and change. So this is pi over 2, pi, 3 pi over 2. That's the range of values that I'm looking for my intersection in. So the only intersection that landed inside of that range of values was this one. So I what?
No, I don't.
Okay. And when I do that, I got about 3.87. Is everybody okay with that? Alternatively, I could do sine inverse of negative 1.5. Oops, that's dumb. What did I forget to do? Needs to be 1 over negative 1.5. So I get this. Not what I'm interested in, right? So maybe I just keep adding 2 pi until I get something that falls in that range of values. Uh-oh. It's too big, right? So again, we've answered the question already using the graphing function, right? We're just talking about how we could have done this without doing that. Well, let's do this then. So we're still kind of talking about 16. Sine and cosine are negative in the same locations, correct? So all silly turtles crawl. The places where sine could be negative is down in here, in one of these two quadrants, right? Actually, we'll just do this. So if I make my two reference triangles, actually, I'm going to color code that a little differently. Oops. I'll do one of them red, and I'll do another one a different color, so it's a little bit more clear. Okay. This one, the green one, is what we found when we did that initially, right? That is our negative 0.7 or 0.730. Everybody's okay with that? Oops. Yeah. So this angle measures our 0.730. Why didn't I care about the negative? Because I'm talking about the angle measure inside of this triangle, which is angle measures are positive in a right triangle, right? So what does this angle measure have to be? Same thing, right? And now I'm caring about this actual angle. So if I add pi to that, there you go. Joanna. Yeah, we can do that in just 1 second, okay? Be happy to look at that. So again, this is just another way of thinking about it. When we start talking about solving, this is probably going to be the better way of thinking about it than having to go to our calculator and like find intersections. But this observation that the angle measure here is going to be the same, that reference angle is going to be the same in each of those right triangles, that's going to be important. It's going to be important. All right. So 15 asks us to do tan inverse of 1.3. So I'm going to graph tangent, not tan inverse, and then 1.3. Because what I want to find out, Joanna, is the angle, all the angles where tangent gives me 1.3. So I have to graph tangent and 1.3 and find the intersections. And those will give me the angle measures that give me that. So we're already on the trig graph, so I'm going to just hit graph rather than zoom trig. So here's my graph for tangent. Here's my graph for 1.3. So again, looking at the x-axis, this is pi over 2. This is 1 pi. This is 3 pi over 2. So the area I'm looking at is just right in here. And I see just the one intersection there. So second trace, intersect command, enter, enter, and now I have to give it a guess because there's lots of solutions here. I got to make sure that I'm close to the one that I care about so the calculator finds the right one. So this is one of the few times where the moving so that we have a good guess is going to be important. And there's my 4.06. Yep. So again, if you're looking for the tangent inverse of whatever is going to give you an angle measure, but to find all the possible angle measures, you need to graph regular tangent and then whatever that output needs to be so you can find all the places that give you that output. Yeah, you're welcome. What else did you guys want to talk about? I feel like there was another one before that you mentioned, list 16, that you wanted to talk about, that we just kind of gotten sidetracked here. Was it 18? Well, let's do it together and just make sure, right? So 18 was cotangent inverse of something of something. Oh, cotangent of cosine of x. All right. So first thing I'm going to do is I'm going to think about x as a ratio. I'm going to think about it as x over 1. So now I'm going to draw a right triangle. I'm going to label one of its angles theta. Relative to that angle, the adjacent side is going to be 1, and the hypotenuse is going to be x. I'm now going to find that third side by using the Pythagorean Theorem. Which is going to be the square root of x squared minus 1. Oh my goodness, guys. What did I do wrong here?
No.
Yeah, how come nobody yelled at me for this? 1 is the hypotenuse, x is the adjacent. So when I do the Pythagorean theorem, I actually have 1 minus x squared, not x squared minus 1. Jeepers creepers, that was close. All right. So what can I say now? I can say that cotangent is just of cosine inverse of x is just really cotangent of this theta. Specifically, this theta right here. How do I find cotangent? Adjacent over opposite, so I get x over square root 1 minus x squared. I do not. Again, I think what we had said was if there were if it was all numbers, we'd worry about rationalizing those denominators. But if it was a variable expression, we wouldn't. I think is kind of where I'm at in this course. What's up? Sure. What was 17? Can you just read it to me? So again, I'm going to start by thinking about x as a ratio. And I'm going to draw a right triangle whose opposite side is x and the adjacent side is 1. Stop talking, please. And then if I do the Pythagorean theorem, I can find the third side is just going to be the square root of x squared plus 1. So I can say now that this is just equal to sine of theta. The theta I'm using is this specific theta in this triangle. That's going to be opposite over hypotenuse. So in this case, x over square root x squared plus 1. Yes, basically we're using the inside part to make our right triangle, and then we're using our right triangle to evaluate sine of that angle that we reference everything to. Sure. That's fine. Nope, you can use the unit circle to do it. That's fine. Do you guys feel okay about this now? Better than before? If it's no, I'd be happy to talk some more. Jack? Yes. Again, like, I asked you to do this on your own, and I did expect you to do that, but certainly if we have questions and we want to do some more things, that's fine. Okay, cosine inverse of cosine of 7 pi over 4. Okay. So, a couple of different ways we could do this. Remember we had said before that we can just say that this is O. Our angle is 7 pi over 4. The issue is that this is not inside of the domain for cosine inverse. So one way I could do this would be adding or subtracting 2 pi from this. What's going to be the issue, though? Still not inside of the range that I need, right? Sorry, that's range. So what should I do? Well, I'm going to just evaluate cosine of 7 pi over 4 with my unit circle. Seven pi over 4 cosine is square root 2 over 2. Okay with that? And now I can go to my unit circle and look at the places where cosine gives me square root 2 over 2. Well, it's at pi over 4 and 7 pi over 4. Agree with that? Well, we've already seen what happens with 7 pi over 4. We can't get that to fit in the interval that we need. Pi over 4, though, does work. So we saw, I think in the example, we saw a case where we could just subtract 2 pi or add 2 pi and make it work. We've seen now an example where it can't. When it can't, my solution was to evaluate the inside piece so that I could then go back to my unit circle or whatever to get an answer that would work. So good question, Jackie. That was decidedly different than the ones we did in the example, so I'm glad you asked about that one. Does this help when I do the problems kind of wrong? And like maybe do what we'd expect to do and talk about like why I know it's a bad answer or what's going on to know that like it's not an unreasonable thing to do, and what to do if you get in a place where it seems like you're stuck, and talk about other things you could do. Okay. Again, if you're seeing something that you did and you're like, I'm stuck at this point, I think I did everything right, but I don't know why I'm not getting the right answer, we can certainly play like that hypothetical game. Like I could ask you to come up and like write up whatever you did, and we can talk about what to do instead or what to do differently, or if there's a mistake in there, what the mistake is. I'm happy to do that kind of thing too, but you got to let me know, because I don't see your homework for the most part. And even then, I'm not really looking fine-tooth comb at it. You know, I'm looking at it for like 2 seconds and then moving on. You know, it's not like I can look at that sort of thing. I might notice the difference between your address and your trig homework. I might. But Jackie, you feel better about that now? Again, anyone else? So the big thing to remember, the big takeaway, sine, we put an angle in and we get a ratio out. Sine inverse, we put a ratio in and we get an angle back out. The problem is this is only one of many angles that would have that ratio. The calculator is only going to give us one specific angle. There are infinitely many angles that would actually give us that ratio. And that's the subtle part of this chapter, is being able to figure out if you have the actual angle you're looking for or not. Okay, so that's going to be a lot of our time and effort is going to be devoted to making sure we can actually get the right angle out of that question. And that's why we looked at this kind of a problem several different ways, because we might need to use any of those several different ways to kind of sort through this. Okay? Let's stop here.